let's do some more series for your response. All right, it's 9-6. So 9 for B, kind of give you a little introduction to what these problems can be like. So the Maclaurin series. All right, Maclaurin series for e to the x is 1 plus x squared root of 2 plus x cubed root of 3, which is 6, which is 3 factorial. That's a series you should have memorized. I guess they're helping us out and giving it to us. The continuous function is defined by, now there's a new function that's defined by this. X cannot equal 1, which kind of makes sense because it would be division by 0 undefined. And they give you some known value, like an initial condition. Function f has derivatives of all orders at x equals 1. All orders means second derivative, third derivative, fourth derivative, fifth derivative, sixth derivative, all the derivatives. So A says, write the first 4 non-zero terms and the general term of the Taylor series for, now this is Taylor series, so this is all the infinite terms, so we should be putting plus ... at the end. Now, it actually says to do it for this guy first, about x equals 1, so that's the center. So they give us this more complicated one to start with, but in the problem, but we're just doing part of it. Now, if you like pain and you want to create your Taylor series, sort of the way that we could create any Taylor series about any center, and I mean, I guess it's hard because it seems like you would have to do it like this. Here's all the derivatives. Okay, they get really messy. And you're trying to do the first 3 non-zero terms, so you have to, or the first 4 non-zero terms, so you have to go all the way up to the 6th derivative. I bailed on the 4th derivative. I mean, it was just an incredible amount of work to do these. So this one's kind of interesting because generally you think of Maclaurin series as always being centered about 0, but because of the way this series is written, the centered at x equals 1 has right there, that's a shift. So that's something that we've looked at before in series, is that you can shift a function to left or right by adding or subtracting something to the x value inside the function. So if you subtract 1, you're shifting it to the right 1. So this would be the same graph as e to the x squared, but shifted to the right 1. So that's a new center. So we're going to take advantage of that. So that's definitely kind of an interesting thing. Now, the point breakdown here is 2 points, 2 points, 3 points, 2 points, for a total of 9 points. So we're trying to do this function here. I guess I shouldn't call it f. E to the x minus 1 squared. The center is a equals 1. So like I said, you could try and go through and do lots of derivatives, or you could say, okay, well, e to the x, which they gave us, if we take that same function and we subtract 1 from it, and we plug in, or actually, you know what we're just do? We're going to plug x minus 1 squared into it. So this is just kind of interesting. So that's e to the x. So e to the x minus 1 squared, we can plug x minus 1 squared into each of these terms. So it's going to be 1 plus x minus 1 squared plus x minus 1 squared over 2 plus x minus 1 squared cubed over 6. And it's the first 4 zero terms plus dot, 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 plus, we're going to plug an x minus 1 squared in for x, and then to the nth power, or in factorial, plus dot, dot, dot. So, I mean, I guess we could write it like that. We could, simplify it. E to the x minus 1 squared equals 1 plus x minus 1 squared. I definitely wouldn't expand the binomials. Plus x minus 1 to the fourth over 2 plus x minus 1 to the sixth over 6 plus dot, 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 plus x minus 1 to the 2n over 2 over n factorial plus dot, dot, dot. Now, they said to find the first 4 non-zero terms, and that is one of your points, 1 point for the 2 correct terms, 1 point for the rest of the terms. So if you get 2 of the terms correct, you get a point. If you get all the rest of the terms correct, you get a point. You also get a point for the nth, the general term. That's the nth term. So that's 3 points, or 2 points. Sorry, 2 points. So 1 point for the first 4 non-zero terms and 1 point for the general term. So, that was kind of weird. I mean, I'm thinking centered about 1, so I actually need to do all the crazy work, but that's just insane. You should not expect to have to do that. Use the Taylor series found in part A to write the first 4 non-zero terms and the general term of the Taylor series for f about x equals 1. So that was part of this series for f of x. Now they're saying write the series for f of x. And what we can do is we can just say, okay, well, let's replace this 1 plus x minus 1 squared plus x minus 1 to the fourth over 2 plus x minus 1 to the sixth over 6 plus dot, 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 plus x minus 1 to the 2n over n factorial plus dot, 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 minus 1 from all of that divided by x minus 1 squared. So we could do that. The positive one and the negative one cancel each other out. And then you'll notice that all the terms in the numerator all have x minus 1 squareds at least. And so we can simplify it. And we get a 1, right? X minus 1 squared over x minus 1 squared plus x minus 1 squared over 2 plus x minus 1 to the fourth over 6 plus dot, 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 plus x minus 1 to the, okay, so this is 2n, so 2n minus 2 over n factorial plus dot, dot, dot. So that's our answer for part B. It is worth 2 points. 1 point for the first 3. It did say 4 non-zero terms. So there is another term we need. What's the next? What would have been the next term? X minus 1 squared to the fourth power over 4 factorial. So we do need another one. X minus 1. That's to the 8th. So it's going to be the 6th over 4 factorial. 4 times 3 is 12 times 2 is 24. Or 24. So we do need 1. So I would have lost a point. 1 point for the first 4 non-zero terms being correct, 1 point for the nth term being correct. One of the main things you got to do is if it says general term, make sure you put the nth term. Okay, C. Use the ratio test to find the interval of convergence for the Taylor series found in part B. So that in itself isn't that crazy. Use the ratio test to find the interval of convergence, the limit as n goes to infinity, the absolute value of. Now it says of the Taylor series found in part B. So there's our general term right there. So we're going to use that. X minus 1 to the 2 n plus 1 minus 2 over n plus 1 factorial divided by the nth term. Now this is going to be 2n plus 2 minus 2. So it's going to be 2n. So rules of exponents. I'm just going to try and simplify this. N plus 1 factorial is the same thing as n plus 1 times n factorial, which cancels with that. Rules of exponents. Say the 2n and the 2n cancel, you have x minus 1 in the negative power, so it's going to be x minus 1 squared over n plus 1. Now, if you take n to infinity, it actually goes to 0, which is always less than 1. No matter what, it converges. So it's kind of rare for power series, for interval of convergence, but it is an extreme case that can happen. So the interval of convergence is negative infinity to positive infinity. D says use the Taylor series for f about x equals 1 to determine whether the graph of f has any points of inflection. Points of inflection. So points of inflection points, happen when the concavity changes signs. So first you want to find where f double prime equals 0 or undefined. Then you want to make sure you verify that it actually changes signs. I mean, that's general approach for finding inflection points. So we have f. We have this series up here on part B. So we're going to find f prime, which would be x minus 1, because the 2 cancel the 2, plus 4x minus 1 cubed over 6 plus 6x minus 1 to the 5th over 24 plus plus 2n 2n minus 2 times x minus 1 to the 2n minus 3 over n factorial plus . Okay, so that's the first derivative. The second derivative, just write it down right now, would be, the derivative of this would just be 1. The derivative of this would be 12 x minus 1 squared over 6 plus 30 x minus 1 to the 4th over 24 plus plus 2n minus 2 times 2n minus 3 times x minus 1 to the 2n minus 4 plus all over n factorial. That's just power rule. Multiply by the current exponent, divide, and decrease by 1. So this is kind of tricky, but let's see. We're looking specifically at x equals 1. This series where the graph has any points of inflection. Okay. If you look at this, no matter what x is, the second derivative is always going to be positive because all the terms that involve x are raised to an even power. And so you're going to, for sure, get a positive result. So f double prime x is positive, greater than, or equal to 0, probably just greater than 0, greater than 0. So concave up for all x. So it's concave up all the time. So how many, does it have any inflection points? Well, if it's concave up all the time, that means concavity doesn't change. And therefore, there are no points of inflection. So that was kind of a hard one, I think. A little weird at first, realizing that we could use a Maclaurin series, even though it wasn't centered at 1, but sort of relating this to a Maclaurin series, kind of just thinking of it as a shift. And then building the more complicated function, that wasn't as bad. The ratio test, I think, was straightforward but the problem is it relied on part B, which relied on part A, and then part D, inflection points. Finding the second derivative wasn't hard, but then being able to understand, make the conclusion that it's always positive, so it's always concave up, so it has no inflection points. That was a little harder. So that was definitely a tougher one. Okay, here's another one. Right, 2007. Let f be the function. So they're giving you a function, and it says write the first 4 non-zero terms and the general term of the Taylor series for f about x equals 0. So that's Maclaurin. And we know, we've memorized e to the x, right? Maclaurin series for e to the x, it's x to the 0 over 0 factorial plus x to the first over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial. Pretty easy pattern. And I guess we could even write plus x to the, now depending on where we start, we could say n over n factorial if we start n equals 0 plus dot dot dot. So that's e to the x. So e to the negative x squared, what we're going to do is we're going to plug negative x squared in for each of these. Now you got to put in parentheses, negative x squared, negative x squared, negative x squared. We'll try and clean this up. Might be helpful for other problems later on. So I'm just plugging negative x squared in for all the x's in parentheses. So if we clean that up, e to the negative x squared, we're looking for the first 4 non-zero terms. So this is 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial. So that's the first 4 non-zero terms. And then it's going to be, we could just write it the way we have right here. Now, a lot of times, this is an alternating series. As you can see, it has a negative. A lot of times we do separate the negative and then the alternating part, which can be helpful. That can make it easier for other things. So that's what we're going for here. That's our answer. The point breakdown here is 3, 1, 3, 2. So points, you got 1 point for 2 correct terms, at least 2 of them. 1 point for the rest being correct. 1 point for the general term. So that's, I don't know, seems kind of, so I don't know, that was all right. B, use your answer on part A. Now this is worth 1 point, which means it's probably some kind of weird question. Don't stress too much about it. Don't spend a lot of time on it, but try it. And then if it feels like it's taking a long time, come back to it later. Now, this involves f of x, which is what we just found. And I think I've shown you guys something like this before. I mean, you might just go ahead and just rewrite it and plug it in, see what happens. So we're going to plug in, so we're going to do 1 minus x squared minus parentheses 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial plus dot 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 plus negative 1 to the n, x to the 2n over n factorial plus dot 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 It's not a Taylor polynomial, it's a Taylor series, so it has all the infinite terms. Let's see if anything cleans up. You got to distribute this. So the ones cancel, the x squareds cancel, and we get the limit as x approaches 0 of negative x to the fourth over 2 factorial minus x, plus x to the sixth over 3 factorial plus dot 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 plus negative 1 to the n plus 1, because we're getting extra negative distributed in there. So an extra negative 1 to the first. So use rules of exponents to combine it with what's there. Over x to the fourth. Now, we could simplify this even further and say, oh, well, we could divide x to the fourth out of all these terms. And that would give you negative 1 over 2 factorial plus x to the x squared over 3 factorial plus dot 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 plus negative 1 to the n plus 1 stays the same, x to the 2n minus 4 over n factorial plus dot dot dot. So I just plugged it in and I am simplifying. Now as x goes to 0, all the terms after this term, 0, 0, all have x's, so they all go to 0, and we get negative 1/2. So that was fine. It was worth 1 point, but you had to have an answer from part A to be able to do part B, so that's the one drawback. Part C says, write the first 4 non-zero terms of the Taylor series 0x e to the negative t squared dt about x equals 0. Use the first 2 terms of your answer to estimate 0 to 1/2. So first 2 terms. So we often use series to estimate functions. And it says if you use the first 2 terms, well, it's like a, whatever order it is, first 2 non-zero, first 2 terms. So this is the function that we just wrote on part A. So if we want to integrate it, we can go ahead and just plug it in. Now, generally we put t's for the inside. If we have x's in the limits, we usually put a different variable on the inside. So we put t's because they shouldn't be the same variable. So the most technical way is we'd write t's in here, t squared plus t to the fourth over 2 factorial minus t to the sixth over 3 factorial plus dot 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 plus negative 1 to the n t to the 2n over n factorial plus dot dot dot. And so I'm writing all these possible terms because it's a series. Series. Right. Okay. So we're going to go ahead and integrate one series to get another series. That's not an uncommon thing. So antiderivative is going to be t minus t cubed over 3 plus t to the fifth over 5 times 2 factorial minus t to the seventh over 7 times 3 factorial plus dot 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 plus negative 1 to the n is just a coefficient, it stays the same. T to the 2n plus 1 over 2n plus 1 times n factorial. And then we're going to plug the limits in, x and 0. If you plug x in, you're going to get a bunch of x's where the t's are. If you plug 0 in, those all drop out. So we get x minus x cubed over 3 plus x to the fifth over 10 minus x to the seventh over 42 plus dot 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 plus negative 1 n x to the 2n plus 1 over 2n plus 1 n factorial plus dot dot dot. Now it says write the first 4 non-zero terms. They didn't ask for the general term this time. Okay. Now we got an answer. Now we're going to use it to estimate zero to 1/2 of e to the negative t squared dt. Well, if this is equal to exact of it, we're going to estimate it with the first 2 terms. which means we're going to plug 1/2 in for x because this represents 0 to x. So we have x's here. So if it's 0 to 1/2, we're going to plug 1/2 there. So it's going to be 1/2 minus 1/2 cubed over 3. That's your answer. We could simplify it. Minus 1/8 over 3/1, 1/2, minus 1/24, 12, 11 over 24. So we use series, Taylor polynomials, just a certain number of terms to estimate exact answers. So, D, explain why the estimate found in part C differs from the actual value by less than 1/200. Why does your estimate differ from the actual value by less than 1/200? You need to realize that that statement right there is asking you about error. Okay? You're trying to find error. How does your estimate differ from the actual value? So a lot of times the way they write this is they say, okay, well, the actual function at 1/2 minus the Taylor polynomial at 1/2, the absolute value of it is less than some value. And this right here represents the error. Sometimes they actually write it like that directly to you, but they don't even say anything about error. The word error was not involved here, so you got to realize they're talking about error. How's your estimate wrong, but less than 1/200? So it's either Lagrange error bound or alternating series error bound. Now, hopefully from your experience, you would prefer to use alternating series error bound as much as possible. And the series that we're dealing with right now is an alternating series. So that's your best bet. Because otherwise, Lagrange error bound, you're going to need derivatives of that function up there. And it's going to be harder, and it's probably not what they're looking for. So, we're going to take the function that we were just evaluating, and it might be nice to write it in closed notation, closed form. It's this series right here. It's x to the, and if we start, I guess it depends on where we want to start. We can start at x equals 1, and it's going to be x to the n over. Now, we got to be careful. If this is n equals 1, n equals 2, n equals 3, you can't skip n values. So it's going to be 2 times n minus 1, 2 times n minus 1, 2 times n minus 1, 2 times n minus 1 over 2 times n minus 1. And it's alternating, so it's -1 to the n minus 1. So that's your closed form. And this is an alternating series. So we could use alternating series error bound. So alternating series error bound is that the error is going to be less than the next term. So if we're using the first two terms, it's going to be less than the next term. And the next term in the series, it's right up here, is going to be x to the 5th over 10, but we're going to plug x equals 1/2 into it. It's going to be 1/2 to the 5th over 100 over 10. And that's going to be 1/32 times 1/10, which is going to equal 1/320, which is less than 1/200. And there you go. But you got to show this. You got to show the work, show what it gets, compare it to the thing they're telling you to verify. So that's alternating series error bound, which is a lot easier than Lagrange error bound. All right, let's do another one. Maclaurin series. So you know it's centered at x equals 0. Where function f is given by, so they give you the closed form on its interval of convergence, it will work. A, find the interval of convergence. Justify your answer. Show your work. So far this sounds a little more straightforward than the last ones. Ratio test. Limit. As n goes to infinity, absolute value of the n plus 1 term, n plus 1, 2x to the n plus 1 over n plus 1 minus 1 gives you 0, divided by the nth term, absolute values. See if we can reduce it. It's going to give you a negative 1. It's going to give you a 2x. We could rewrite it. Limit as n goes to infinity of absolute value. You put the n minus 1 over the n, and the negative 1 and the 2x. And this is going to go to 1. So you can get the absolute value negative 2x, which is the absolute value of 2x, which has to be less than 1. So a lot of times I divide out any constants, coefficients for an x. Absolute value of x is less than 1/2. This is your radius of convergence. If they ask you, I'm going to tell without actually finding the interval of convergence. I mean, you're so close though. X is between negative 1/2 and positive 1/2. Now you need to test the endpoints separately for intervals of convergence. You need to make it very clear which x value you're testing. Rewrite the power series as a number series. So I'm taking this series and I'm plugging negative 1/2 into it. Now, negative 1/2 will give you negative 1 to the n minus 1, which will give you negative 1 to the 2n, and that would give you positive 1. So you get 1 over n minus 1. This series, if you write it out, if you start at 2, it's going to be 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus ... That should look familiar to you. That is the harmonic series. And if it's a harmonic series, then it diverges. So I'm fine with that. You could try other approaches. You could rewrite this starting equals 0, and then it would just be 1 over, or n equals 1. Just be n equals 0, it'd be 1 over n to the, like if you write this, n equals 0, be 1 over n to the, just trying to think now, n equals 1. Then you'd be like, oh, that's an harmonic series, p series test, integral test. Okay, let's try x equals positive 1/2. I feel like usually a common result is a lot of times one endpoint results in an alternating series, which are easier to converge, and one end doesn't. So that one didn't. So I'm thinking this one might be an alternating series, which has a little more likelihood of converging. So if we plug this positive 1/2 in, we get negative 1 to the n, positive 1 to the n, over n minus 1. 1 to the n is just 1. This is an alternating series. So the alternating series test, I guess if you start writing out, it's like alternating harmonic. So you could say that, show that alternating harmonic converges. Or you could do the nth, or not the nth term. It passes the nth term test, but that's inconclusive. But alternating series test, says if it goes to 0, then it converges. So your final answer is going to include positive 1/2. Parentheses, brackets. That's, that's like work we've done a lot of. The point breakdown here, by the way, is 5 and 4. So that was 5 points right there. And after the last 2 problems we did that were a little weird, this was a refreshing, straightforward part A right there to get 5 points. B, show that y equals fx is a solution to the differential equation xy prime minus y equals 4x squared over 1 plus 2x. It says for absolute value of x less than r, where r equals the radius of convergence. Okay. I'm just writing that information down. Show that y equals fx is a solution to the differential equation. Now, we know how to solve differential equations. It's how you undo the derivative, you separate the variables. I'm not sure if we would be able to separate the variables here. We're not trying to find the solution. We're trying to show that that the function we already have is the solution. Now, verifying that something is a solution can be different or maybe easier than trying to find the solution in the first place. So let's see. We have y equals fx already. They said y equals fx. Y equals fx. And fx is the function that was given to us at the beginning. And we could find the derivative of it also. So y equals fx equals n equals 2 to infinity of negative 1 to the n, 2x to the n over n minus 1. And we could just start writing it out just to see what it's like. If you plug a 2 in, it's going to be positive 4x squared over 1. And then you plug a 3 in, you get minus 8x cubed over 2. And you plug a 4 in, and you get positive 16x to the 4th over 3. You might be able to start predicting this. 4, 8, 16, 32, x to the 5th over 4, and so forth. So that's, we could write the general term as the term that's already written in the closed form. Okay, so I just wrote that function out just to kind of see what it looks like. And let's find we need the derivative. So let's find the derivative of y. So it's going to be f prime x equals. Now, when we take the derivative, we can take the derivative of the closed form, and the negative 1 to the n stays the same. It's just a coefficient. The 2 to the n would stay the same, unless you really want to do chain rule. I'd separate that. The x to the n, so a derivative, you would multiply by the current exponent on the x and decrease it by 1 over n minus 1. So that's sort of the closed form. On these individual terms, you can just straight out take the derivative, 8x minus 24x squared over 2 plus 64x cubed over 3 minus 160 x to the 5th over 4. And the nth term would be what we just figured out. You'd have a 2 to the n, then n times x to the n minus 1 over n minus 1 plus ... So I wrote out the y as if it were a function. I wrote out y prime. And then we're supposed to be able to plug this into here. Now, all right, well, let's try and construct that and see what we get. Okay, so this is definitely kind of weird. Part A was pretty straightforward. Part B is kind of a little weird. So xy prime sorry, xy prime would be what we just came up with, but it would be 8x squared minus 20, minus, let's say, 12x cubed plus 64 thirds x to the fourth minus 40x to the fifth plus dot 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 plus negative 1 to the n times 2 to the n times n times x to the n minus 1 plus 1, because we're multiplying by an extra x, over n minus 1 plus dot dot dot, so that'll just be x n. So that's x y prime, and then we're going to go ahead and subtract y from it. Okay, so if we subtract y from it, we're going to subtract 4x squared minus 4x cubed plus 16 over 3x to the fourth minus 8 x to the fifth plus dot 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 plus negative 1 to the n, 2x to the n over n minus 1 plus dot dot dot. And we have to distribute all that multiplication. So we're building some crazy series right now or something from these other series. And so we've done this quite a bit. So what do we get when we do this? Xy prime minus y is going to be, if we use y equals fx as a solution, then it should make this true. I guess that's what I'm hoping to prove. So I'm working on the left-hand side, see if it comes out the same as the right-hand side. So what do we get? We get 8x squared minus 4x squared is 4x squared minus 12x cubed plus 4x cubed is minus 8x cubed. Positive 64 thirds x to the fourth minus 16 thirds x to the fourth is plus 48 thirds, which is 16x to the fourth, minus 40x to the fifth plus 8x to the fifth is plus 48x to the fifth plus dot dot dot. And so how are we doing here? Now this is where it gets a little weird. You're like, okay, all right. Now the other thing you got to think about, that I'll say this is definitely hard, is that this, you might think, if this is some kind of series, maybe this is, if this all equals this, then this is the sum of that series, right? And the only series that we've really talked in depth about the sum is geometric series. Can you think of this as a geometric series? Now, if I have x's in it, that's a power series, and that's kind of how we created our first power series, was by looking at geometric series and plugging x's into the common ratio. But if you look at this, we're multiplying times negative 2x times negative 2x times negative 2x. This is totally a geometric series, right? So this is a geometric series with r equal to negative 2x. The first term is 4x squared. The absolute value of r, which would be the absolute value of negative 2x, has to be less than 1. Okay, just in case we need that. The sum equals a over 1 minus r. Hey, and so it's going to be 4x squared over 1 minus negative 2x. And so we get 4x squared over 1 plus 2x. It totally worked. 4. Now remember, the same thing as absolute value of 2x is less than 1. Absolute value of x is less than 1/2. So I mean, we could say that. Or we could say this. So there you go. It says where the absolute value of x is less than r, the radius of convergence. And what was the radius of convergence? Way up here. 1/2. And here it is, 1/2. So that was definitely challenging. All right, got one more. Let's see if we can finish it before my video stops. Predict that we only have 10 minutes left. All right. So function is defined by the power series. They give you power series, open form, closed form for all real numbers for which a series converges. Find the interval convergence for the power series F. Justify your answer. Show your work. So A, ratio test, limit as n goes to infinity, absolute value of x plus 1 to the n plus 1 over x plus 1 to the n. So here's a rare case where the expression for the nth term is in a fraction, so we don't have to do times the reciprocal. Rules of exponents, so this is the limit as n goes to infinity of x plus 1, which is just x plus the absolute value of x plus 1, because there's no more n values, and it needs to be less than 1. And so we could do a little ruler postulate if you want. Take away 1, negative 2, 0, less than. You need to test the endpoints. Okay, always got to do endpoints on interval of convergence. So x equals negative 2 gives you number series n equals 0 to infinity of negative 1 to the n. And that's going to fail the nth term test. So show the work, name it, show it in its detail. Doesn't equal 0, diverges. Okay, so then we'll try the other one. X equals 0. Write the number series from the power series. If we plug 0 in, we get 1 to the n, which is just 1. So this is also going to fail the nth term test. Write it, name it, show the work, show why it doesn't pass. So the answer is negative 2 to 0, or negative 2 to 0. So that wasn't bad. The point breakdown, by the way, is 3, 1, 2, 3. Okay, part B, the power series above is a Taylor series for f about x equals negative 1. Find the sum of the series. Now, it says that it's about x equals negative 1, which would mean like the center. And that kind of makes sense with what they wrote. You see a bunch of x plus 1s, and it's usually x minus the center, right? And they're saying that we need to find the sum. So now power series came from geometric series, and you can see that the series is times x plus 1 times x plus 1 times x plus 1, right? So that's the common ratio. The common ratio is x plus 1, which is what we got here. So r equals x plus 1, and we're trying to find the sum of it. So the sum equals a over 1 minus r. The first term is 1 over 1 minus x plus 1. Make sure you put in parentheses. Is 1 over negative x. So there you go. Did I make a mistake up here? Okay. All right, I got 5 minutes. C, let g be the function defined by. G is a function that's an integral of another function, which is something we started seeing in Calc AB, but now we're seeing it with series quite a bit. And they want you to find g of negative 1/2, which means if it exists, or explain why g negative 1/2 cannot be determined. So maybe we should first try this, negative 1 to x, and the function f is, let's see, well, let's see. Now I'm getting stumped. So we just got done proving on part B that this is the sum of the series of f, which means that it equals this. So we can put negative 1 over x in here into this, or put it with t's first, I guess. And then we integrate it, and it's going to be negative natural log of the absolute value of t. And then this is a definite integral. So it's going to give you negative natural log of the absolute value of x minus negative natural log of the absolute value of negative 1 plus plus. This is going to be 0. And so we get negative natural log of the absolute value of x. Then it says to use that to find the value of g at negative 1/2. So it's going to be negative natural log of the absolute value of negative 1/2. It's going to equal the negative natural log of 1/2. And that's your answer. You could also write it as, you bring negative 1 and call it natural log of 2. So that was kind of weird. And then D, let h be a function, hx equals f of x squared minus 1. Find the first 3 non-zero terms and the general term of the Taylor series for h about x equals 0, and then find the value of h1/2. So we already found, we already have this function up at the very beginning, and we're going to plug x squared minus 1 in for all the x's. X squared minus 1 in for all the x's. So I'm just going to write that first. So you guys should be used to plugging one series into another, or one expression in to get another one. So what do we get? If we simplify this, we get, let's see, this should be a plus 1. Minus 1 plus 1's all cancel out. So we get 1 plus x squared plus x to the 4th plus dot 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 plus x to the 2n plus dot 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 equals the summation n equals 0 of x to the 2n. So we just plug in x squared minus 1 in for all the x's. And so hx equals 1 plus x squared plus x to the 4th. Find the first 3 non-zero terms and the general term. So there we go. And then use it to find the value of h1/2. So that means we're going to plug 1/2 squared, or 1/2 in for x into f, and that's going to be 1/4 minus 1, which is going to be f of negative 3/4. And we already found the value of f of x, the sum of f of x in part B. So it's going to be 1 over negative 3/4, which is 1 over 3/4, which is 4/3. There you go.